Hi, we have been working with vectors for quite a while now, so it's about time that we start to take a look at the calculus with vectors. What we're going to start with today is the limit. And what we should find out is that the way we take the limit of a vector is the same way as we would expect as when we took Calc 1. So this is basically our Calc 1 lesson right here. And the only difference is, remember, when we look at a vector, we have to look at the x, the y, and the z components independently. So that's exactly what we're going to do. We are going to treat the I, the j, and the k components independently from each other. So let's take a look at an example. We want to find the limit of this vector as x approaches 4. So from Calc 1, we're going to take a look at the I component first, and this is saying we want the limit as x approaches 4 of sine of x minus 4 over x minus 4. Now this may look a little hard for you, but maybe you might recall a rule from calculus that says the limit as x approaches 0 of sine of x over x is 1. Well, this right here, this x approaches 4, this is just a horizontal shift. And if we shift this back to the left 4 units, this will become 0, and that will become 0. So this is just equal to 1. Now, if you don't remember this rule, that's okay. We're going to talk about another way we can solve this in just a few moments. The next one we're going to take a look at is the limit as x approaches 4 of x squared plus 1. And this is just our substitution. We would get 16 plus 1, which is 17. And then the last one, this one looks pretty nasty here, the limit as x approaches 4 of x minus 4 over 1 minus e to the x minus 4. And if we plugged in the 4, we would get this 0 over 0. And you might recall that this is what we call indeterminate. It's at indeterminate. It's at 0 over 0. Therefore, we're going to use L'Hopital's rule. Now, unlike when we took the AP practice, we don't have to write all those long sentences anymore. So that we got that going for us. So we can just take those derivatives. We would get the limit as x approaches 4. The derivative of the top is just 1. That's what L'Hopital said. The derivative of the bottom is just going to be e to the x minus 4. And if we now plug in the 4, the top becomes 1. The bottom becomes negative 1 because e to the 0 is 1, and we got that negative. So we get negative 1 right there. Now, like I said, if we had trouble remembering this one, if we plug in the 4, we would still get 0 over 0. So that's also indeterminate. So even for the top one, we could also use L'Hopital's rule too. All right, remember, L'Hopital's is when we use indeterminate. And there are two indeterminates. So we have 0 over 0 or infinity over infinity. Then we can use L'Hopital's rule. So our answer then is just going to be 1, 17, negative 1. And remember, this is what the values are approaching. And that's, remember, what a limit was. It's not what the value was, it's what the value is approaching. Because we really can't approach 1 or negative 1 because those two are undefined at 4. So it's what we're approaching. So this might be a hole or something there. Okay. So let's review some derivatives. So we can also calculate the derivative of a vector as well. If we have r prime of t, and this is what it says here. I know it's kind of hard to see that, but this is r prime of t is equal to the derivative. And again, notice we're taking the derivatives of the I, j, and k components independently. Now, if you notice, they can use chevron form, or you can use the I, j component form. So we can either use, of course, the chevrons, it doesn't matter, or we can use the component forms. Either way is okay for us. So let's look at a quick example. We have r of t equals this cosine of t 2t plus 3, natural log of t squared plus 1. Remember, this is a trace, and if you forgot what that is, I have another video on that. But a trace is basically, it's the two-dimensional intersection. It's a two-dimensional image. Or it's like, we compared it earlier to like a spiral. If you have, like we talked about the toilet paper roll of mathematics, right? We had a toilet paper roll of mathematics, hard to see there. But a trace is basically a line that I trace along a path on that toilet paper. And in this case right here, it becomes a spiral. So it's like a two-dimensional line on a 3D image. That's basically what a trace is. So we want to find out how that trace is changing, because remember, that's what a derivative is. So to get r prime of t, we just take the derivative like we normally would. The derivative of cosine is negative sine t minus 1. The derivative of 2t plus 3 is just 2. Natural log. Remember the derivative of natural log, if you forgot that one, the derivative of natural log of x is 1 over x. So this becomes 1 over t squared plus 1 times, don't forget chain rule, 2t. And there's our derivative right there. Just like we did a long time ago. Very simple to do. Okay. Now I know what y'all thinking. Man, this stuff is pretty easy. But how is it going to help me with my equations of a tangent line? I'm so glad you asked. You might recall, to get a tangent line, there are two things we need. One, we need a point. So to get the point, we need to look at the values at 4. So we want r of 4. And I'm going to plug it into the OG. So this becomes the cosine of 3, because 4 minus 1, comma, this becomes then 8 plus 3, which is 11, because 4 times 2 is 8, plus 3 is 11. And then we get the natural log of, again, this becomes 16 plus 1, or 17. And there is our point. Next, we need a slope, but we don't call it the slope with vectors, we call it that direction vector. For this, we need r prime of 4. So now we're going to plug that into our derivative. So we get negative sine of 3. That's just a constant, so it's just going to stay 2. And this becomes 8. 2 times 4 is 8 over 17. Now, writing the equation of a line back in pre-cal was calculus was easy. So calculus 1 was pretty easy. We would just do y minus y1 equals mx minus x1. In multi, it is a little bit different to write a vector line. In multi, we're going to use this. Now, it's a different symbol. It's the tangent line at t. Now, t, of course, stands for the tangent line. You can use a different variable, but they do tend to look at this. The tangent line is equal to the following rule. It is going to be the slope at 4 of t plus the original point, plus our starting point. It is kind of the same here. It is the same. The only main difference is our starting point is basically 0, because remember, if we think component form, we're looking at starting at the origin. So it's just a quicker way to write this. So therefore, we would say t of t equals r prime of 4. So it's going to be this negative sine 3, 2, 8 over 17 t, because this is my slope, t, like my y equals mx plus b, plus r of 4, which is cosine 3, 11, natural log 17. Ran out of room right there. And there is the equation of our tangent line as a vector. A vectored line. So, alright, go on to part 2. We're going to take a look at a few more examples. And we'll take it through. Thank you.